And your position is.
And we are recording. Yeah. Espérate, el micrófono, Max.
Ah, yes, it's here. Asegúrate que está encendido. Póntelo en la camisa cerca sí, ahora sí. Yeah, now it's on.
Yes.
Okay, so now put it there because some speakers yesterday
I
you
know,
only had them part of the time.
I know. You guys see me?
Now it works. Yes.
Almost.
Okay. Well, still people are coming in, although we're already 2 minutes into the program. All right, so we're already 2 minutes late, but today we're going to keep to time because of the evening lecture that we have at the end of the day. By the way, regarding the public lecture this evening, it was completely full, and then we sent an email to register participants saying if you are not coming, please cancel. And they're having a small number of cancellations as a result. So if anyone wasn't able to get an electronic ticket, you may call your mobiles now. I don't think all of you will be able to because it's only a few, but you may call now and I'll try to secure one. Go. Good luck to you. Let the best win. Well, and if you don't get one, keep trying because in the day maybe someone cancels and you get it. All right, so it is my pleasure today to introduce Joaquín Fernández Rossier, who is at the University of Braga in Portugal, and he's going to talk about bottom-up design of quantum matter with nanographenes.
Okay, thanks a lot. Good morning, everybody. Thanks for being here. So, being out there enjoying London, which is one of the best cities in the world, right? Thanks to Jorge, Quintanilla, and Chris Coleman and the organizers for inviting me and really to be here in this conference. Okay, so Jorge, I'm going to correct you. There is no such thing as University of Braga. I know it's in Braga, in Portugal, indeed, but it's okay, so the title of this talk you can see there, right? It's a bottom-up design of quantum matter with nanographenes. Okay, so I'm a theorist. I'm an experimentalist, and I'm going to tell you right now in the first couple of slides, I'm going to spoil my own talk. It's going to be a summary. Okay, I hope that will not discourage you to keep watching the talk. And now I need to be able to move my slides, which is okay. So talking 2 minutes. Here we go. Okay, so I'm going to be showing this type of molecule, nanographene. This is a graphene fragment. Okay, I'm going to
sharing your screen.
Too many things. I have to use the laser, and what else? And I'm sharing my screen. Apparently, I'm not. Okay, we share it again.
Somehow we lost it, yeah.
How about now?
Compartir pantalla.
Yeah, I'm sharing right now.
Let's try to stop. Oh,
No, I'm sharing now.
okay.
Am I?
Okay.
Thanks, Jorge.
Yeah, and if you can use that, even if you cannot turn the slides.
No, don't worry. I will use the laser, but
Yeah, just use it as a laser.
yeah, no, that's I can do it. Okay, so let's go again with my 2 minutes scenario. It's okay. I'm going to be discussing nanographenes, mostly in triangular shape, like this one in my favorite, a spin one, and that way in the top. This animal can form chains. Okay, and in this configuration, there are a couple of magnetically, so this will form a spin one chain as Haldane studied in the 80s. Okay, and by means of spin spectroscopy, that shows both the gap that has liquid and condensed peaks at the side. These are the.
Inelastic.
No,
that's not.
This is inelastic.
Oh yeah, so it's not a gap. It's actually the inelastic.
It's a gap in the spectrum of inelastic excitation. That's what I meant. Thanks. Okay. So we see. You see the spectrum different molecules in the chain. In the side units, you see condensed peaks, compatible with having a spin 1/2 excitation there, as predicted by Haldane theory. And in the central chains, you see a gap in the elastic spectroscopy. Okay, so finally we're having a Haldane gap. Okay, and then encouraged by this success, okay, I will discuss our predictions for two-dimensional lattices of this. Right. So far, moving the slide has been challenging, but yeah, let's see. Okay.
You don't think this is, do you think this is full? Do you think this is spinning? Spinning.
Yeah, that's why. I mean, the claim is that these are the one molecules, they're from spin chain, and then they have then Heisenberg spin model.
Right, so these are spin excitations.
Yeah.
And that's why there are these shoulders, which are probably another.
You have fine structure here, you have many of them.
Yeah.
And I'm not in the middle because it's like up. Yeah. You'll see details later, right? You will listen. And then, time permitted, I will discuss our predictions for two-dimensional lattices of this triangulate at two levels. Okay, already at the non-interactive level, the bands of these animals are uniform and they have flat bands and they are narrow. So in the flat or they have narrow here. So very much in the spirit of treated by layer, but these are made with bottom-up approach. Okay, we can predict what is going to happen very easily, actually, based on the symmetry of the one functions of the molecular orbitals. Okay, and now when we plug in interactions, this is what we promise, we find two kind of things. One is kind of not super interesting, but it's still worth talking about, anti-magnetic order. Okay, but the other kind of ground state that we could have, in particular in these lattices, where these larger triangulates have spin 3 halves, the ground state that might happen is the very famous very small solid created by AKLT-type. Okay. And okay, so this will be discussed at the end. And now to honor the statement of Pierce on Monday, that one of the main topics of this conference is quantum information. There's a connection between this AKLT ground state and quantum information. It was found by these researchers, okay, Wade, Ian Africa, and Robert Rossier. They show that the ground state of the AKLT model is this very special type of state. It's a universal result for measurement-based quantum computing. So if somebody could have a system that is described as Hamiltonian, the ground state of the wave function would be a very good starting point to do measurement-based quantum computing. Okay, it's still not an easy task for us to discuss, but it wouldn't be a bad thing to have. Okay.
So, I mean, what do you mean quantum computational resort? What exactly?
So this strategy for quantum computing, which is based on starting with an initial state, is very special because it has the following property that if you do only readouts on specific qubits and single qubit operations, you can implement any quantum algorithm. Okay, so you are basically trading the need to do 2 qubit gates, which is harder, by the need to prepare an initial state, which is very special. And then the ground state of this Hamiltonian gives you this type of ground state for free.
So the way that you can do those computations around that.
Yeah. Well, that's to downplay the high expectations about it. You still would need to do something. You do a readout and then you should cut the interaction. Okay, so that's kind of hidden in the papers, but I'm not telling this anymore. So
cut the interaction between the qubits.
yeah. So yeah.
So we should do like a sort of like in
But-
between qubit number one.
Yeah. Anyway, that's all. So yeah. So that's all.
Switch on to other interactions. This one is
I will show you that these interactions come out naturally in these systems. And that's what will spoil my talk. I will go on for coffee. The magnetism of the nonlinear fence is going smaller than we need, but we are getting new systems now that are closer to what we need. Okay, so let me move on. So that was the connection with quantum information. So the whole spirit of this talk is the following. I feel like a little kid. Okay, as a little kid, I used to play a lot with Lego, or the study version of it. Anyway, so here my Lego pieces are the nanographenes, and we can make toys more and more complicated. Okay, and I will show you the kind of games we know how to play. Okay, but in the discussion, I would love to hear from you other games you could play with these toys, because somehow what I'm telling you is all news in the area of quantum magnetism, and I'm sure many of you know more than me about new ideas, and maybe some of them can be implemented. Okay, so this should go both ways. That was my 2-minute summary, which was like 10 minutes now. So the important slide of my team, you see the young people, the PhD master students here, the senior guys. Let me tell you who has done the work on this particular project, okay? And also, let me include here ex-members that have been involved in the project. Okay? So mostly Gonzalo and Ricardo, and now in the team, Joao and Mark and Antonio. Okay, these are the key players here. And very important also, we're collaborating with other theorists and with experimental groups of Chilean Feld, who is the chemist exploring the chemical synthesis that makes possible to do this wonderful molecule, and Roman Fassel, who is and Pascal, who is the leaders of the social science team that use a steam spectroscopy to measure the properties of the molecules. Okay. Here Shanta was PhD student who did the measurements for the Haldane excitations. We'll see later on. Okay. Okay. So for the motivation, I think this is the spirit of the conference. Right? We in the title of the program is quantum materials, and in my mind there are two different times. Those happening naturally, whatever that means. Okay. And for instance, cuprates or superconductors that we talked about yesterday, right? And also heavy fermions, okay? And well, here, the challenge for theories is to understand data, okay? As you can, you know very well, it's very hard, okay? Another strategy is to make artificial materials, artificial quantum materials, where you put larger pieces, larger effective atoms like quantum dots, supermassive qubits, in more layers, okay? So then your effective atom is a bigger structure, and ideally, the theories will be able, or that over time, to predict what is going to happen. Okay? So then to design to engineer properties. Okay? Maybe that's impossible, but that's what we are trying. So one challenge in this second strategy of artificial quantum matter is the following: that is, artificial atoms are very identical, that bring disorder into the game. And also, since the energy scales scale inversely proportional to size, bigger atoms mean small couples. Yeah. Well, molecules are identical, but transmoles are not identical, quantum dots are not identical. Yeah. Other systems. Oh, you see, you spoiled my. Yeah, you guys are really smarter than me. That's okay. So natural solution molecules, okay. So and this is like you already saw. So we're going to use molecules to do bigger structures, okay. Now the nice properties of these molecules that will become self-evident as we go, okay. Well, they're scalable in the sense that we can do monomer, dimers, trimers, chains, rings, even some crystals are already being demonstrated experimentally, okay, 2D crystals. The speed of tunable, I would argue that the speed of the molecule is linearly proportional to the size of the tangle in it. Okay. And we have already demonstrated non-trivial quantum effects like this very long solid and the personalization given by operated by Haldane. Okay. And as anticipated already, the 2D crystals are tunable. You can decide what type of flat bands they are going to have. And there's potential for non-trivial quantum state like the big answer. Okay, so that's the.
So I have a question. So you already have enough thing of exploration. This was the one at the end of the chain you were talking
Yeah.
about. And you know that it's skillful and it's the right spinning.
Yeah.
You know it's skillful.
We know, I mean, we know that we know two things. There's a gap in the excitation. The individual molecules have spin because they show Congo, and theory brings all of that. Now we can compare very carefully the spectroscopy of chains of different lengths of triangles in theory, at different levels of theory, and get a very good agreement. And in particular, we see the two main features that matter for the spin chain. We see a gap in the elastic spin excitation spectrum when you park your tip on the middle of the or away from the edges, and we see quantum peaks on the sides that only happen when the chains are long enough. So we see all you expect from theory. Okay?
Yeah, but Lamb is fractional relation. It's still fraction.
We don't see the fraction. We can discuss this. We're proposing experiments to measure the with STM-ESR the absolute value of the magnetic moments of the states of the chain. So in principle, it could be measured. In this experiment,
Yes.
we don't really show. We don't have they have not implemented yet absolute measurement of magnetic moments. So in that sense,
Yeah, for instance, magnetic field or something, it's not split in the
that's not been done yet. So far, what are we discussing? The topic is spectroscopy. So this is evidence of an object that is able to give you a zero bias peak.
So exactly, this is exactly the place where my RAM is stored on the railroad, right?
Yeah.
Otherwise, speak is one thing. I'm not saying it, you don't have it. I'm just saying actually, you're setting up bar very high.
You are right. So that's why we're thinking of an experiment where we would settle any possible alternative discussion. And the other thing is that like the mathematics, there are not many. I don't know any other alternative explanation to this. Okay? So that's and then we don't have Microsoft giving us 60 million bucks to do anything. So let's take out how it goes. Okay? Somebody got keep them funded because they claim my grant. So we didn't get any funding. So yeah, come on, go out. I mean, I didn't say that. Thanks for asking. I mean, so everything, most of the stuff I'm going to say was with other shapes. Okay. I will show at the end other shapes. Okay, I realize actually have included a couple of molecules in my first slide. There are other shapes. Okay, and triangles are have a few advantages. Like you will see them as we go. Okay. But there are other possibilities. It's not only about angle. That's important. So thanks for asking. You can have spin one with different shapes. Really simple. Physicsin is good for some stuff we'll see. We make it and deal with it. Right. The smallest is not in the screen. If it's spin one, the smallest would be just this. That will be more half, yeah. We are very interested also, and it is also in the being measured, and I'm showing some data now, okay?
This is what you get from the order your slide.
Well, but that's good, I got the data, so
So obviously this reminds a bit of single molecule magnets, which are usually some rings with some metals and then some organic stuff. And in those cases, you get a huge separation of time scales. There's a very strong interaction between spins within the molecule and often negligible interaction between molecules. So here I get it that that's not the case, right?
yeah, just to give you a number right away, the coupling between these two spin ones is like a 15 to 20 millimeters. Okay, and the magnetic result is usually C. So these guys are very well described with AKLT-type models, Hubbard models.
And you don't have electron mobility between them.
Yeah, and there's this coupling between them, which of that.
Yes.
The way they do it is like this. Okay, they deposit some precursors on a gold surface. Now they hit the precursors and they self-assemble. So it's not like a real manipulation. So the time scale for this is whatever is the chemical reaction of the minutes. Okay. Yeah. Okay. Good. So, okay, let me say a word about the methods. Other algorithms we see fall into some of these categories. We always start with some Taiwan calculation or some different calculation. We identify molecular orbitals that are relevant for hosting the magnetic moments. Okay, that depends on the reduced Hilbert space. And within this reduced Hilbert space, when it's small enough, we can do a full renormalization. For bigger systems, we do DMRT. And our model, by the way, most of the time is Hubbard model. Okay, and then once we get the low energy states of a given structure, often we derive a spin Hamiltonian. Okay, and then we compare the predictions of these calculations with STM spectroscopy of two types. In this talk, I will focus only on this one, on the inelastic electron spectroscopy, no time to discuss ESR. Okay. An important remark is that for some of the most interesting effects, we need to go beyond the field, we need to go beyond DST. Okay, you cannot describe Haldane insane with mean field, or I don't know how to do that on this. Okay, so this is the structure of the talk. I will now go to give some details about the electronic structure of one molecule, two molecules. Then I will show you the chains of theory and experiment, comparing each other. And then at the end, when we have time, I will discuss the theory for the student stuff. Okay. So the theory, the starting point is the same Hamiltonian we use for graphene. We only consider one atomic orbital per carbon, the PSB orbital. Of course, the edges of the molecule, we assume they are highly related, so for example, binding bonds and anything like that. Okay. So you have the same Hamiltonian you have for graphene, but it's not two atoms in a itself. You have it for this guy, 22 atoms. Okay. You solve it numerically. And then you get negative energy states, like in graphene, it's a bonded states, they are occupied. You get positive energy states also, in graphene, these are empty. But you get something that you don't get in benzene. For instance, you get the state at zero energy. Okay? And these are the main characters of this talk. Okay, so let me tell you the properties and the origin of these zero modes. Okay. So there is a theorem that tells you how many such states, zero mode states, will you have if you have a bipartite Hamiltonian. And of course, the whole of is a bipartite lattice. That means that you can assign fake colors to atoms, red and blue, and the third tables of blue atoms are all red. Okay, so that's a bipartite Hamiltonian, and now we can count how many red and blue atoms you have. And there's a theorem that tells you that you have at least as many zero energy states as the difference in the number of A and B sublattices. Okay? So for this triangulation, the difference is 2 and you get 2 zero modes. So another important property of this zero modes is that unlike the bonded and antibonded states that live equally in the two sublattices, the zero modes live only in one sublattice, which is the magnetic sublattice. So here we're looking at the wave function of the two zero modes. For these molecules, we have C3 symmetry, we choose the zero mode when they're degenerate, and we choose them to be eigenstates of the C3 symmetry. Okay, and we'll come back to these cases later on. Okay, there's a second theory for Hubbard models with interacting electron in a bipartite lattice at half period. This is super famous Leaves theorem. And this theorem also is about the sublattice imbalance. And now what you get is the spin of the ground state of the Hubbard model for the positive interaction. Okay. And again, it's given by so twice the spin is given by the sublattice imbalance. For the molecule sublattice imbalance is 2, so the spin according to this theorem is 1. Okay. So now I'm going to show you calculations of this question at the end. Can you go again?
What are the arrows?
Okay, yeah, I will discuss out later. This is the face of the wave function. I'll play some more later on.
So I look at this green plot. Would I be able to tell the zero modes allocated? I have wave function, or I have states. I can do that the states are real space,
Yeah, this is a real space representation, right? So
where it's all over, it's not overlap.
they tend to be going the edges, but here in this molecule, this is exactly what you get. Okay, you get bigger balls in 6 locations in the edges, but they're also inside.
Yeah.
You will see other cases where they are farther away. They're not literally, they're not edge states.
Or maybe for big enough, it will be down in the state.
They belong to the same, everything I say for these guys is the same that these guys are the same. Okay? But yeah, okay.
Yeah, question about this. You've got 2 theorems here. One is a one particle theorem about the one particle wave functions. And the second involves how you entangle the electrons in those states.
Yeah.
What I would have thought this is the kind of Hooke's rule coupling you've got in here, but you said you were using the Hubbard model,
Yeah.
which there is no Hooke's coupling. So
There is some coupling when you think about it in molecular orbitals. When you represent the Hubbard model in the molecular orbital basis,
yes,
you naturally get effective ferromagnetic interaction between orbitals that are on the same line.
I got it. Okay, that's right. Thank you.
Yeah. So, but the theorem is really powerful. I mean, you can make sense of the theorem exactly as we just did, but for other cases, I don't find I don't understand way out. For antiferro cases, for instance. So
These more sets in genetics, they're not units. Of course, they won't.
yeah, I mean, these are the question about the ground state of the Hubbard model, or
No, these elements, we each have the spin up.
yeah, sure. This is a spectrum in one spin channel. So if you want to spin in terms of filling, you would have to have all of these guys doubly occupied, and then the last 2 electrons would go here, and then you have a half full shell connecting with Kuhn's question of Pierce. Okay. Yeah. So, but indeed, these 2 theorems are superficially look alike, but they are very different animals. Okay. For instance, the non-interacting one we can show in one line. The other is not so easy. Okay. So this is the outcome of a real calculation. So this is the theory I was saying a second ago. Okay. Now what you're looking at here is the energy of the excitations. No, the energy of the states after solving the Hubbard model divided over the single particle space made by these 2 guys and these 2 guys here. Okay, we're reducing the different states, and then you get a ground state compatible with the theorem spin 1. Then you get a excited state with spin 0, which is half a volt above. So the intramolecular state is gigantic. Okay. And then you have higher up states. Okay, so bottom line, the relative state is spin 1. We have done this with many different approaches, quantum chemistry, mean field, you name it. It's extremely robust result. Okay, that's not dependent on details. Okay, you can actually check out the newspaper here. So, and what is the magnetic moment? Now, after the interaction, the magnetic moment goes to the edges, which somehow reminds the edge magnetism of graphene. Okay. So, so the magnetic moments are living in extended areas. They are not like living in one atom.
Sorry, can I ask a question? Hello.
Yeah, there's a
Yeah,
question.
yes. So can you go back to the last slide? Go back
Back
to
one
the
slide.
yeah. So what's the meaning of these arrows on this green 2 green graph?
Oh, the arrows in the single particle orbitals is the phase of the single particle wave functions, and the other arrows, the big arrows in the 3D plot, is the magnetic moment of the ground state in one of the 3 projections. The projection with the symbol 1.
Basically, these 0 modes, they are on the edge, right?
They are in the edge. They are not exactly where the 0 mode is. There are some differences coming out from the interactions, but there's a big overlap. Most of the magnetism lives on the 0 modes.
So this big graph are on the edge. I can see the spin density, right? Those are spin density.
Yeah, the top triangle with the arrows is the spin density.
I think they are from the 0 modes, right? as you plot.
Mostly from,
the-
yes, mostly from the zero modes, not uniquely, but mostly from the zero modes.
Okay, but these phases, so these are from tight binding model, right?
Yeah, the phases are not spins. They are the phases are here, right? If you see the formula for the wave function, right there,
Yeah, but
the
you-
amplitude in the phase. So what I'm plotting here is this angle theta in the single particle wave function.
okay, so but your Hamiltonian is tight binding model, right? T
The-
is real.
Yes.
T is real. Then-
Yeah.
Then how do you get this phase factor?
Oh, because you have two degenerate modes, and I choose them to be eigenstates of the C3 symmetry operator. When you do that, this particular linear combination of zero modes comes out as a complex number.
Oh, okay.
Okay.
Thank you.
Question in the back?
Yeah, but this is already many by, right?
Yeah, yeah. Our U's are typically in the range of the Haldane. The Haldane is 2.7 electron per carbon. What does it mean about it? The U's, this is a U meter. When we can go always compare DSP and mean to Hubbard or exact Hubbard, and then we can say, okay, the U that would resolve is in this range, and the range is always between 0.7 and 1.5 in the Haldane, okay? That's what we have. So, okay, so far we discussed only the animal here, okay? The three triangulated, three because we have 3x and 1 on the side. But of course, you can have smaller, so that I was asking before, and bigger. And now the two theorems we discussed also work here, so we can do the math. We will have a similarity imbalance of 1, so we'll have 1 zero mode, and we will have spin 1/2. This will have isolated imbalance of 3, so 3 zero mode, 3/2, and so on. Okay, and now the good news is that this has been done in the lab, different groups in the last few years. Okay, so what we are looking at here are different either SPM or FM units of the different molecules in different sizes. So these are by now made, and the dynamic obstacle to make the molecules is the following: the presence of these bonds make them extremely reactive. So for many decades, or many chemists either didn't have interest or didn't have the know-how to make these molecules because they were so reactive, they would lose it to some other object. Okay. Now the trick here is to keep the molecules in ultra high vacuum and to do the final steps of the synthesis on the surface at low temperature, on the ultra high vacuum surface in a non-reactive surface like gold. Okay, that's why people have managed to do these molecules. Okay, there are other tricks, but this is the key one. Okay.
Is there a very nice theory? Is there any experimental tests that can be used to confirm these spins of these
Yeah.
structures?
Yeah.
What is it?
Well, let me show you right now. Okay, so at least to give you a hint. Okay, this is not gonna give like the spins. This is what they have. Okay, so for instance, the two smallest ones. This is the DIDV taken with STM bias, and this is for the spin one. Well, we think the spin 1/2 triangle. And now you have the gigantic condensed for spin 1 triangle. You have also zero bias. Something we do calculations. We do solver for spin level, and you get a condensed peak also for spin 1. Whenever I see a zero bias peak, I will call it condensed peak even if it's.
Can you show that they split into the appropriate number of constituents in that thing?
That would be great, but the way to do this and to prove this with the elastic spectroscopy requires that the Zeeman split is larger than the alignment. This kind of thing has been seen for atoms on surfaces where the atoms are decoupled in the substrate. But here the molecule is very on gold, so there's an implicit lining of the steps that is bigger than Zeeman splitting. So they have not seen that. Let's give you further information. Chemists have been able to do these molecules in crystal, okay, adding extra groups to protect them from chemical reactions, and then they do ESR and then spin 1. And then there's actually a very recent paper where the molecule is almost identical to the guy in the crystal, and they get ESRs now, compatible with the spin one. Okay, it's in a buck. Okay. So yeah, I think we are relatively safe ground. Okay. Okay, I think we are going to move on now to the second part. Let me take time. How are we doing time-wise? Okay. So far it was only discussion, not the real talk started.
Yeah, of course. Yes.
No, let's see how we make it. Okay.
I'll let you know when there's 20 minutes left to really finish.
Okay. So dimers. So with dimers, well, then the dimer, this is an AFM image, very convincing, right? And this is inelastic spectroscopy. So remember, the blue line is DIB, the red line is the derivative. So what we see clearly here is a inelastic excitation at 14 MeV. Okay. So, well, for those of you who might not know what inelastic spectroscopy, let me remind you. So the idea here is the following: the electrons can go from tip to sample elastically, that always contributes, and also inelastically. So that means that they go from here to here and from tip to sample, and in the middle, in the molecule, they excite something, photon, spin, plasma, whatever. And that opens a second channel for transport. So that means you have two circuits in parallel, so that gives you extra conductivity, hence changing the flow, change in the step in the derivative. Okay? So presence of steps, symmetric in bias, and positive and negative, is a clear indication that there's something inelastic going on. Okay. So now I'm going to try to convince you that this is magnetic origin. Okay. So the way we think about it is like this. Okay. So first of all, let's see if this is compatible with theorems and such. Okay. So one of the two triangles should have spin 1 on their own. When we put them together, the symmetric imbalance of these two guys compensate. Okay, one has more blue atoms, the other has more red atoms. All together, they have no excess. So this theorem will tell you these two objects are spin 0 objects. So a natural possibility that the two spin ones are forming a spin singlet. And the excitation they see here is as excitation between spin 0 and spin 1. Now moving on to the magnetic field and see 3 steps here. That was seen in the manganese diamond by Davian and those kind of group a long ago, but the thing is that the line width here of these steps is larger than the splitter. So they cannot do that, okay? Okay, now let's see if this number is something that you can pull out with theory naturally. They can go down to less than 4 Kelvin, but the problem is not the temperature, the problem is the increasing lines. There's a line with the broadening here is larger than thermal. Okay, and again, we think this has to do, well, we have to start that this has to do with coupled gold. Okay. So let's see if these numbers make sense. Okay, so well, let's look at the single particle theory to see whether the original picture of the zero mode provides. Okay, and importantly, it does. The single particle spectrum has 4 zero modes. Remember, I told you the minimum number of zero modes would be given by the subatomic imbalance. So in principle, we might get 0 zero modes, but that's the minimum number. Actually, there's 4 of them, and it's very easy to see what is going on here. The original zero modes live there, okay? They don't live in the binding site. So when you put these molecules together, we ignore thermal copy. They don't hybridize. So you get 4 zero modes, and well, that's a good place for the electrons to be and do their thing, okay? And now we do a mathematical calculation, and for the molecules to talk, we need to include not only the zero modes, but also these 2 orbitals there, okay? The 2 molecules. They're running some sort of glue for the interaction. And this is the result of the manual calculation. Energy levels as a function of Hubbard U. The ground state is always spin 0, okay, in compliance with the theorem. And now we get a first excited state with spin 1 and a second excited state with spin 2. And importantly, the ratio of the energies comes out on a almost a 2-to-1 ratio, which is exactly what the Hubbard, sorry, what the Haldane model predicts. Okay, so in summary, the Fermi calculation gives you as an effective learning model a Haldane-type. Okay, and this is true. Let me insist when we build the neighborhood, something that we are gonna show between a couple. Okay, now we know better. So with this picture, with this value of u, which is like the 4 by 27 times the Hopin, okay, like 1 point something. We get additional agreement with the experiment, and we say, okay, this is it, okay. And this picture, even if it is incomplete, it's true, okay. This is the two molecules have the magnetic moment, and they are counted down.
Can I ask about these 4 zero modes?
Yeah, sure.
So, if they're exactly 0, there should be some symmetry argument for why they're there, right? I was trying to understand it because we've broken the C3 by coupling them together.
Yeah. So naively, we can make it without seeing the argument. I mean, they don't live in the binary side, so they're gonna stay.
Is that
No.
statement true by symmetry? So does the wave function
Yeah.
have to be 0? Okay.
So at the single molecule level, whether symmetry, it is true by the following arguments. When you go through the theorem that tells you that the zero modes have to be there, they have to be in the minority sublattice. And now things are such that for the molecule, the binary site is in the minority sublattice. That's a step. But there are symmetry can also protect zero modes. There are theories about that. It's beautiful. You can discuss all the question.
Yeah, just to follow up, is it maybe just that this model has like chiral symmetry, so symmetry that anti-previous with the Hamiltonian?
Absolutely. The origin of the zero mode is chiral symmetry. The sublattice operator anti-commutes the Hamiltonian. So everything I said about this theorem is chiral symmetry.
And these 4 states all have the same eigenvalue on the chiral operator.
Exactly. That reinforces every chiral operator.
Okay.
Yeah.
So just something that probably is implicit in what you've said, but the fact that you can use the same arguments for the 2 molecules suggests that it's not a good idea to think of a spin residing in one molecule, a spin residing, and then they interact. The spin resides along the whole edge of this.
You're right. The picture is that you have, I mean, the robust picture after all the theory refinements that we see now, have spin 1, 2 spin 1 have interacting. And now the galaxy is going to entangle with my phone. Well, I mean, it's not that you have. Let's discuss about that.
Yeah, let's discuss it later.
Yeah, but I mean, the idea want to imprint in the brains, if you allow me to is that for all practical purposes, this molecule we have a spin 1 object, okay? And the interactions are Heisenberg plus some nonlinear term and one of them. Okay? So, I will show some slides later, but they put some precautions on the surface, complicated, okay, after many steps of organic synthesis. And these precautions are non-radical, they are spin 0. They are present both, and now they hit the surface and they react. And they self-assemble and form a structure unit C, okay? Person for organic is no, I'm the wrong guy, okay? But this, I mean, they have been working on the field of atomically precise synthesis on graphene nanogravhenes, and I think structures have been defined for by 13 years now, maybe more. And people who are really good at doing structures on the surfaces. No, exactly. It's not Manhattan style or Danaher style of moving atoms and they chemistry is very important. Organic chemistry. Okay. So this we saw already. This is the summary of this. Let's keep it, but it should be super clear. So let's move to Haldane spin sense. Okay, so let me briefly remind you Haldane ideas. Okay, so you have a spin 1 Heisenberg model with anti-magnetic interaction, and now Let me do Haldane in the super brute force for dummies version, which is the one I understood. Okay, Haldane did it in a much more elegant manner. So let's solve this numerically. Okay, so the second organization of the chain. Well, first a ring, so no like this, and then we compute the energy of the lowest energy excitation. The constant can be ST01, and now you get the for even chain, for even number of chains is ST0 the ground state, and the first excitation is ST1, and well, the gap goes down and seems to converge, and that will be the Haldane gap. Okay, you repeat the same exercise for a chain. You get something different, okay? You get that your spin one excitation goes down in energy and it feels like an exponential. Okay? So you get some sort of emergent length scale that was not written down in the Hamiltonian, and did and here in the ring you get an emergent energy scale that was not written in the Hamiltonian. Okay, the Hamiltonian has no length scales or no energy scales other than a global constant. So now you go so the low energy spectrum of the chain has a singlet and a triplet, which in the thermodynamic limit become the dynamic. Okay. Now when you look at the states of the triplet, whose average magnetization is non-zero, for instance, the SC plus 1 in a super long chain, this one with the energy, you get that the magnetic moments live on the edges, and since this entire cloud should have 1 unit of angular momentum, you have half of it in one edge, half in the other, and this is fractionalization we discussed earlier. That's my roots for an elegant way of talking about this. Okay, so so this is something for me. It's like magic. You start with the spin one Hamiltonian, and out of the blue you get spin one half degrees of freedom. Everything in the low energy manifold is as if you have two spin one half electrons living in here. Okay, so now let's have a look on the experiments. Okay, so these are the precursors we have discussed right now. Okay, they hit them, and then you get from chains. And what you're looking at here is the different structures. Actually, for them, it's easier to have them in labs. Okay, so it's a primer, tetramer, pentamer, 6, 7 dimer, some very long animals. So sometimes they get lucky, they get rings, it's 40-something units. Okay. Now they go, they part the STM. By then I mean from Fassel here, Haldane and Mishra was doing most of the experiments. And what I'm going to show you right now is two sets of spectra for two different structures. Same and a ring. Okay. So every spectrum here is a DIDB taking one molecule, and they, except for units 1 and 16, they look pretty much the same. This shape region is meant to say that there are no excitations there, so that would be that. But of course, the big deal is that the difference is that in the chain, in the first and in the edge side, is the zero bias speed that we interpret as having a condo peak, because there's a spin on half of the localized on the edge. Okay, so so this is the deal. Okay, so this suggested that there is a spin on half object there. So now, just to see how robust is this picture, since we cannot have split peaks in magnetic field we discussed, the best way that we use to compare theory and experiments with many units. Okay, and then initially we started with our original Hamiltonian, the Hansen Hamiltonian, and we were getting the right line shapes. I will tell you about it in a second, but the energies were off by 20%. That's why after figuring out, we found out that having a nonlinear exchange would be off, and then I will tell you how we can demonstrate that this nonlinear don't have to be there, being derived from a Hubbard model. Okay, so let's go for that. So as I said, we can compare trimers, well, you know, okay, many structures. So the black lines are the spectra, the brown lines are the radial spectra. And what the theory gives you, the Hamiltonian will give you both the energies of the excitations and the wave functions, and they enter into the theory like this, okay? So you have this formula for DID where the energies go here into step functions, okay? And the height of the step function that depends on where in the chain you are, depends on the greatest elements. Okay, so that the theory, when you compare the, what is the second derivative of the current, as a function of energy on one side and as a function of location, the other will give a map of the vertically where are your energies, and horizontally as we move along a given side. So this is some of the excitations are absent in some atoms. Okay. Yeah. I'm gonna stay with that. These guys would be the eigenstates of the Hamiltonian, and now this formula is basically technical and good calculation of current. Okay. So let's set up the state. Okay, so you have the electrons in the tip can go to the surface and vice versa. And they can go not in the spins, or they can go in a common interaction with the spins on the chain. So this again, this Hamiltonian, which is the couple between the spin of the tangent electron and the spin of the chain, okay, of a given side of the chain. So by Fermi-Golden rule, you have to have a square of this object in the theory, and here you go. You have the square of the spin operator. Oh, yeah, the high dependence is proportionality factor here, right?
That magnetism itself is because it's constant interaction.
No.
Maybe for the form of returning an electron with localized speed. So the assumption is once electron have the peak, it's always done right.
I mean, there is this represents indeed you the fact that the hypothesis goes down because the effective coding interaction, which is it's a coding interaction where the initial state of the electron is in the tip, the final is on the surface, and has to go.
Some localized state, having a spin-field interaction, and then going into the continuum.
Right down the Hamiltonian.
Yeah, the Hamiltonian, this is the Condo Hamiltonian.
It's Haldane or
It's of the Condo. So you have electron in the tip, okay? Condo with the spins in the surface, okay, and then electron in the surface, okay? And this direction Anderson, this is all different, okay? So no, we're applying non-stop.
That's fine. I didn't understand.
Okay, so but the point I do what I mean is that the theory gives you two things. One is the obvious in the investigation. The second is not self-evident. In that it is a map. You are at a given energy here, vertical energy. This was something we did for a different paper, a different system, but it is so neat and I'm trying to one here. So the you park at a given energy, and then you have excitations all over. But at a different energy, for instance, in this one, the excitation is missing in two sides. Okay, so that's what I mean. The map. We can map the excitation. What I was telling you is that we started with our naive Heisenberg model, and the maps were good. I mean, the wave functions were good at this level. The energies were off by 20%. Okay, and then we found out. By different methods, we were comparing the calculations of the Fermi Hubbard model for Devers and Finders in the spin models, and then included the neighborhood object that's going to be followed in a second. And we found out the Hamiltonian that would do the job had to have an extra term. This is non-linear state, which is exactly the one in this. square operator is the one getting the AKLT Hamiltonian. Now, the parameters that we do the job with, and we see they work, I insist, they work same for, okay? Where these two, okay? They linear change 90 MeV, and the beta parameter is 0.09, which is like 1/3 smaller than the AKLT part, okay? In 1D. So with this Hamiltonian for the timer, we want to compare with all the structures, and I'm going to show you the comparison after I answer the question. Yeah, so let's have that. This is, if you put second level hopping, then your single particle Hamiltonian is no longer chiral, it breaks electron from symmetry. So when you add in the electrons there, you're gonna be either you're gonna be doing something, you're not accumulating electrons in some atoms because you have broken electron from symmetry. And nature doesn't like that. When you because nature likes to have the same charge when you have an atom. By nature I mean realistic fundamental calculation. So when you're doing your model, you basically should not have second level hopping because when you add interactions in the right way, this is offset. So one way to think about it in a many fashion would be that the self-rate is associated to long-range Coulomb interactions, going to cancel out exactly the second level hopping as to keep the charge neutrality of the carbon atoms. Yeah. We need to kill the second level hopping. Okay. So not here states it is. Now let me show you some comparisons and we move on. We have 20 minutes for our coffee break, Jorge. So
I was going to give you 2 more minutes before I give that one.
yeah, okay. Anyway, yeah, just showing here what I just said. Okay, this is for a theta and four units. Okay, and you see there are 2 clear steps here. There's one more there maybe. And this is the second. This is the scalar plot where the intensity means the second derivative. You having seen that here, we need to have a peak in second derivative or a dip that means have a step in the first derivative. But you can see, right, this pattern is given both the fermionic level and the effective linear to quadratic model. So this is spin model, this is Hubbard model, and the big picture is consistent. Okay. Now,
Question, these Hubbard model calculations, can you do them also for the very big change that you saw in the previous slide?
with some caveats, we can go up to I don't remember anymore, maybe 9. But there are some tricks. There are some theory tricks there. Okay. But yeah, we did. We have to. Yeah, the bigger the chain, the lower level we can hold numerically. Okay? So for the biggest ones, we have to do spin models. Okay, now this graph here. Okay, one is experiment, one is theory. Let me remember. I have put it in the calculator, but I keep copying the wrong one. Okay, so this is probably experiment because I have way less points. Okay, here we have tons of excitations. The size of the symbol, the blue symbols are for chains. The crosses are for rings. Okay. So first thing to notice for crosses, there are no low energy states. Okay, this is your Haldane gap. Okay, now the blue symbols, you have these branch here that you start up here and you go down with some zigzags. Okay, and also the experiment. Okay, the primary is special. We can discuss it. The primary is here at zero because it's a spin one object and it shows a velocized point cloud. Okay, this guy is such its own discussion. If you don't look at the timer, basically the loading excitations experimentally and theoretically are going down, and in the experiment only in the 9, they hit 0. 0 means 0 bias column. Okay. So this is the picture, and I hope you agree this a consistent overall agreement. Okay, and we'll focus the details on small structures as I did in the previous slide. They're very good. Okay. I don't think the agreement is perfect. not the whole story, but the details of the story are I think quite solid.
Can you remind us again how the experiment like site was done?
Oh yeah, sure. They will. Let's go to one structure here. The tetramer, okay. So they recorded the IDV, and now they identify this as a step that gives you the energy presentation that goes with the board. Okay, a second step, second energy. Now it's yeah, very good, very good.
But in some of those you have like 10 points, you know, 10 steps.
In some of them, yeah, let's see. In some, yeah, and so you can have more. Like here, okay, you can see.
Yeah.
I mean, the first derivative is hard. In the second derivative, you can see the case, okay? Yeah. Okay, so now, okay, let me make the big dramatic statement here before we move to the final part. So what I really like of this experiment is the following: we start with an object which is spin one molecule, and then we build a structure that has properties that are missing in the object. Okay? So this is the emergence. We're still we're crossing the emergence from here. The property of having empty states is a property that belongs to the sample. That's not belongs to the unit. Now what I like is that this shows that you can do a bottom-up strategy. You can start with building blocks, then bigger. Well, then this happens. It doesn't matter on a reaction. Still, you can identify the point that means something collective missing on the units happens on the sample. Okay, the point here happens to be at 9 units. Okay, so it's small. But that's why I think this strategy would work for bigger systems. Okay, with different properties. And that's what we're going to discuss right now. So let me very quickly, before I show you the two-dimensional stuff, discuss the origin of this nonlinear state. Okay? And this is something we put in the guide recently done by Joao Carlos Enriquez, a PhD student in my group. And well, so far we were ignoring the third neighbor hopping. And we cannot ignore it. We know this from DFT. I will show you later also. If you ignore third neighbor hopping, you have this 4-0 mode. We already discussed this. These are the wave functions. Okay. Now when you switch on the third neighbor hopping, now I'm putting this third neighbor hopping for you. Okay, these big lines of third neighbor hopping, so you can see how they connect the otherwise decoupled 0 modes. And then in the spectrum, we get some splitting here. And the wave functions look now like hybridized. You get bonding and anti-bonding states. Okay. So now we're going to build a Hubbard model represented on the basis of these guys. And we're going to derive an effectivity model treating this hybridization, this third neighbor hopping hybridization as a perturbation. Okay. And so when we write down the Hamiltonian in the molecular orbital basis, we get 3 types of terms: the hybridization terms, the Hubbard repulsion terms that we discussed briefly with Pierce at the beginning of the talk, and ferromagnetic. No, this is the ferromagnetic Coulomb sample. This we didn't discuss about this obvious, but we put 2 electrons in the same orbital. Let's have a part. So hybridization, Hubbard, stance. This is the Coulomb system. So now, if we treat these guys as perturbation, initially we set it to 0, so we have 2 independent tangulins in the spin 1 band state. Now we sit on hopping, and we derive the Hamiltonian. Let me skip this guy. And then, no, let me not skip it because there's something important here. So there are 3 energy scales in the problem, right? Hybridization, raised to T3, effective Hubbard, which is raised to atomic Hubbard, with some of the factors that are given the wave functions in the orbitals. And then the state, but the states for this molecule is identical number-wise to the effective how are you, okay? And now then these three energy scales depend on two parameters, how are you and degree, okay? So we and the whole thing maps to a closed ladder, okay, with Hubbard interactions and intra-brand ferromagnetic states. So now we derive the model for solar perturbation theory. You get this model, and now you get J with an expression that, well, it's amazing tool there, it's the tau square over U, very familiar to for United States, except for the factor. There's a correction, okay, for fourth order perturbation theory. And now for B, the first contribution to non-United States is to come from fourth order perturbation theory. Okay? So the non-United States is really exotic animal. It's a fourth order perturbation theory based on a third level obviously. It's not the obvious place to look at, okay? And we with the standard numbers, and this is our definition for J from the ratio of non-linear and linear states, and this is what we got from we have got before from our fitting on the Haldane text, okay? So this is probably a good job to explain what is going on there. So now I'm gonna move to the 2D crystals. Do you have any question at this point? Mm-hmm. Yeah. Correct. Yeah, actually, yeah, great. So yeah, both of them are there. So we're gonna do the calculation including all of the packets. We put all the states in the level copy. As a function of U, we do a curve. Okay, and we can say, okay, for this U, we hit the right number. In this particular calculation I just showed you, we are not doing in the slides, we are not doing that. Okay, we are only taking the minimal basic set. So to answer your question, which one is dominant? This one is dominant. Okay? Yeah.
You give me J, and B is about 1/10 of J.
Yeah, so
It's because and J, you pick up J already in the second order, the fourth order get B, and you still get only 1/10.
yeah, because I mean the ratios, I mean the scheme is the right one. Okay? The tau over U is your remember this is tau.
T squared over U equals B. And in the most, that's what it's.
This whole thing is 28. Maybe. Okay. The rate is something like 18 and 2. Okay. So
18 and 2.
yeah, I'm making this up. I mean, this is the I have the number in my mind, but this is yeah. So okay, to the crystals. So we consider honeycomb lattices. So the itself has two triangle units. Okay, we can take the 2, 2, the 2, 3, 3, 3, 4, 4, and these are gonna have different properties. And I'm gonna tell you how to think about it. Okay, so with the theorems again, we can play the game. Okay, so this guy should have still 0 according to the theorem. And now and then also in terms of the number of 0 modes, the theorem tells you that you are not entitled to have any 0 mode. That's what happens in practice. Okay, again, if we know T3, we know by now that the molecular orbitals have many dice. So every time we need to have a single 0 mode, you will have a macroscopic number of them. You will have flat bands. Okay, and actually that's how we got into this. We wanted to have this flat band at 0 energy, and then from DFT we got something else. That's why we started thinking and we still was solved with the level of idea. Okay? So okay, how we do it time-wise?
Well, you could wrap up in 5 minutes.
I'm gonna do that.
5 minutes for questions.
Let's do that. No matter what I wrap up in time. Okay. So I'm gonna show you now because we are all tired, right? I need a coffee. So just to motivate you that we are not crazy. Okay. This is a preprint posted by in Berkeley. 5 months ago, 6 months ago, they're showing something that starts to look like a two-dimensional lattice of triangle crystal. But this guy has 4 lenses, so this is the 4th triangle, okay? So this should be distinctly house. So, so this is going in the right direction, right? So now the key idea I want you to remember from this part of the talk is the following: is that very much like we can understand the three properties of solids based on the symmetry of the atoms, the spherical of the orbitals involved in the bonds, the bond, P1, and so on, okay? And the filling and the dependencies, okay? Here with triangles, we have similar set of tools. We have the symmetry. We don't have SP and D. I'm gonna show you we have three possible values for the supreme quantum number, 0, positive, and negative. Now, for triangling, the dependency given by the number of bases minus 1, or 1 electron, 1, 1, 1, 2, 2, 2, 3, 3, and so on. And the filling we don't control unless we get or we don't, okay? It's half filling. These are the rules, okay? And what I'm going to show you is that the starting point in this crystal for the generalization of the super well-known honeycomb theory for graphene. We're able to have fermions with a flavor inside, and this flavor is governed by this symmetry, okay? So that's the key idea for this bands. Now, so the key symmetry here is a rotation of 120 degrees, and you can, so for when you have only one zero mode, it comes naturally out as an eigenstate of this operator. The eigenvalues of this operator are the roots of the cubic roots of 1, okay? So basically, omega can take 3 values, 0 plus minus 2 by 4, okay? When you have 2 zero modes, like in this, well, maybe they don't come out with symmetry, you need to enforce it, okay? And then when you do that, you get to the function that somebody was asking before, by assuming. For the 4 times, you have 3 zero modes, and again, we choose them to be eigenstate of the symmetry operator, then this is what we get, okay? And now let me show the relation between the arrows and the phase. The red cases are those where the three equivalent sides keep the same phase. So this is a 0. The blue guys, the phase between 3 equivalent atoms is advancing, and here is going backwards. So there will be these 2 guys here. Okay, so this was the deal with the phases, and this is gonna determine the properties of the bands. So when we ignore the neighbor hopping, as expected, we get 2 flat bands, 3 flat bands, 4 flat bands, depending on the number of zero modes in the unit itself. But that's boring, and that's not what we got with DFT. We got something else. Well, boring but interesting. Okay, you have flat bands and zero energy. That's interesting. So in DFT, we got this. We got like a honeycomb, okay? And then we figure out that we put neighbor hopping, we will get the same in the Riemann model. And that now you can understand this very easily. You have 1 zero mode per triangle. You put neighbor hopping, they hybridized, and we get an effective honeycomb lattice for the zero modes, and hence we get the graphene type of expression. But notice the boundary is much smaller. We get narrow band effective graphene, okay? And same gain with the bigger animal. DFT gives it very beautiful bands, flat bands at finite energy, and in the middle, the graphene-like bands. I'm going to wrap in 2 minutes, okay? Wrap up in 2 minutes. Then we're having the same story, and when we ignore it, we get 4 flat bands here. So we could derive an analytical model based only on the zero modes and the symmetry, and this is the DFT, and this is our analytical model, okay? So so we understand this thing in terms of symmetry. So now this animal, the 4-4 is different to all the others. All the others were graphene-like bands at zero energy. The 4-4 has a gap, okay? And now we can even understand the gap in the following manner. we can organize our zero mode not as C3 symmetry state, but also as corner states. Okay, this that would be more in one corner, the other corner, the other corner. And ideally, if there were only corner-to-corner interactions, you would form only bonds out of the corner states, and then you have a gap and no dispersion. It happens that there's an extra hybridization from the distant corners, okay, and that gives the dispersion here. Okay, but this is a very big problem. So I'm gonna wrap up the part I didn't you don't get to see. It is the interaction. And all of that, maybe you can ask me questions about it. But I hope I have convinced you that we can design very interesting states with nanographenes, in particular with triangles. Okay, so I'm gonna stop here. Thanks for your attention.
Thank you very much. Yeah, great, Lego. Can we have 3 minutes for any more questions from the audience? Yes, yeah.
I'm just curious if anybody had tried to build these radios on any other substrate.
People is trying to use copper, and we successfully put in copper. Yeah, there is a okay. There is a strategy that's in my future of life. So I'm you're asking. People have done the following: you grow some sort of actor, and then you grow a filter with gold on top. Still, for the purpose of still proximity, okay. And now you can do the synthesis of molecules there. And for reasons I don't understand, this is not working so well. But people is trying to do this. Now also, there's another way of doing proximity superconductivity here. But it goes on graphene. You can put lead islands on top of graphene and superconductivity laterally. I always do this on the top, that's happening. Because we do not have the boundary, it's magnetic, and it's a sugar state. That's something. Other stuff.
So this modeling neglect the coupling to the bone electrons, right? But it still works pretty well. You understand what is the role of the electrons of the coupling? I think it's not going to go.
Yeah, so let's see. So in what I show, we definitely don't include it. We have done the calculations where we do okay, and of course there is a lifetime that is reduced because harmonization with the goal. Okay? Something that worries us a lot when doing coupling. We found that the effect is very small, and the reason the following is that the type of stereo coupling we use on graphene on a surface, the so-called AKLT-type, which is coming from the symmetry, and effectively on the time ground, this gives you a first level spin plate coupling. And all these zero modes that are between one angle for the electron, we don't want some lattice. So to read longer, this first level coupling does nothing. The first level arrival does nothing on the zero mode because they already want some lattice.
It's the spin orbit, but what about the lifetime?
The lifetime is definitely doing something that's you can see experimentally. There is some data which is for example very soon. You can have the same molecule on gold or on top of an array of silicon line, and then that shows you narrower steps in spectroscopy and also different energy. And we understand the different energy because there's a normalization of the we have a spin chain from the coupled to electron path. The excitation units are normalized. Okay. So we think that these different energies for the same molecule of different substrates or different substrates to reduce current interaction.
It's still kind of
All right, this is getting very, very dangerous. This is a very detailed conversation that let's have over coffee. And I am conscious that I know that to one last question, so you can keep it very quick, and then we break for coffee.
In order to enhance the beat, to get to college with those one community, maybe this is at least from the radical perspective. But it should be the silicon atom should be find a way to deform the orbital in a way by changing the sensitivity of structure to make it
We are going to play the game right now. So there are two things we can do that are kind of working. One is to take the shape, as you were asking earlier. The other is to go these guys in a smart way. But this is so recent I cannot talk about it. I will be breaking many secrets. All right. We found one that really encoded in large linear states completely out. It's replacing carbon atoms with some of the atoms.
Okay, this is now canceled by the clock. So we now break for 20 minutes and we're going with